Okay, good evening. This is ProfDavidJDelosReyes. Okay, it's October 12, 2023. The time is 9:13 p.m. Okay, my topic for this session will be a continuation of my AC machines, okay, long video format discussion, and we are now on lesson number 38. Okay, and the title of the subject matter will be, we will be solving an example problem involving the concept of stepping down concept. Okay, let's proceed. The topic for tonight will be alternating current machines, lesson number 38. And the contents of the topic will be example problem, okay? The problem is with regards to the so-called stepping down concepts. Okay, stepping down. The last time around, the topic that I discussed or the example problem I gave you is actually the so-called stepping up. So for tonight, it will be stepping down. It is the reverse of the last topic. So we could visualize the importance of the so-called delta to Y connection or Y to delta connection. So at least we now know where the connection Y delta or delta to Y is being used. Okay, let's try to read the problem, or I will try to read the problem. 3, the ratio 30:1, step-down transformers are connected. The configuration is Y delta, meaning the primary side is Y connected, and the connection of the secondary is delta. For stepping down, the 132,000 volts, they should be plural, volts, 3-phase transmission line voltage. If we try to figure out the verbal statement, or the previous verbal statement, we are given a transmission line. Okay, I put one line here, then I mark this was it will be one like that, and I will place 3 like that, meaning to say this is 3-phase. Okay, so you will not draw all the lines, because if you try to draw all the lines, it's a no good design. And under the so-called design of circuits, if we draw a line, for it to be a 3-phase line, we mark it like that. Okay, so this is a transmission line. The voltage line to line of the given transmission line is 132,000 volts. For this 132,000 volt to be used to a safer value, we must have to step down this voltage here. This is very big, right? Imagine the primary of your transformer is 130,000 and the output is 120. There's a little bit discrepancy, right? So we must have to bring down this 132,000 to a certain value. Which is safe to the clients, right? Okay, I will try to read again the problem. 3 30:1 step-down transformers are connected Y delta for stepping down the 130,000 volts 3-phase transmission line voltage. So this emanates from the power plant. Okay, the power plant send the voltage generated by the alternator through the transmission lines. Okay, and at the end of the transmission line, okay, which is connected to a post, which is a wood post. It's not anymore a tower, right? It's a wood post. We call that primary lines. And connected on top of it are actually 3, okay, single phase transformers, 3 step-down transformers. So meaning to say, connected in the post are actually 3 transformers. Okay, they are what you call this single phase. But according to the given problem, the connection is Y delta. So to satisfy this Y delta, you must have to interconnect these three transformers, so it will look like a Y on the primary and delta on the secondary, and we could do that, right? So we are not talking of a single, what we call this three-phase transformer, which is bigger, okay? Because actually we could create a transformer which is just one, but it will be three-phase. These are just single phase. I think this is more flexible than this one, because this one three-phase transformer, if you try to put it on the post, it's very heavy, right? It's very heavy. So if you try to replace this big transformer by three single phase, okay, the weight will be more manageable, you know. So in here, there are three single phase transformers here, and according to the problem, calculate the secondary line voltage. We need to step down this 132,000 by using a Y to delta connection. Okay, so according to the given problem, if the voltages between lines on the primary side is the side that comes from the transmission line. Okay, because this transmission line is fed to the primary of the transformers on the post, right? And the given line-to-line voltage is 132,000 volts. The problem is asking if the connection on the secondary side is delta, okay, what will be the line-to-line voltage there? Is it safe enough now to be what they call this handled by the electricians? Okay, because we do not convert this 132,000 on the primary, then we'll make the secondary 120. Okay, it's too far. It should be 1,000 volts also. So we will convert this 132,000 to a certain 1,000 voltage. And again, this 1,000 voltage 2540, upon reaching the secondary post, we'll be having again a single phase transformer, in which the primary is 2540 and the secondary will be 120. So the main purpose of the so-called stepping down is actually for the primary input voltage on the distribution transformer to be lesser, and it is safer for house customers and for the electricians. So upon stepping down the value from 132,000, it becomes 2540. Okay, the transformer that will go to our houses will now have a rating. The primary will be 2540 and the output will be 120 if you are in the USA, right? Also, I am just giving you a preview on how we are doing the stepping down for the voltage of the primary of the distribution transformer to be a lower value. Because if you put this 132,000 here, you know, there's a problem. So actually, we are stepping down the voltage to a certain value, which is safe to the, what they call these electricians and the house customers. So upon reaching the secondary post, the primary input voltage now will be 2540 and the output will be 120 if you are in the USA. Okay? Okay, I will try to erase this one. But I will draw it again. So the primary will be 2540 and the secondary will be 120 and this will go to the houses. Okay? Okay, let's go back to the figure of the given verbal problem. So we are given a transmission line. The line-to-line voltage is 132,000. And at top of the primary line post, which is made of wood, are actually three single-phase transformers. Okay? With the configuration Y delta. Okay? The problem is asking what will be the line-to-line voltage of the secondary if the connection is delta. And on the primary side, it is Y. So this is 132,000, this is 132,000. Okay, so before we could compute for the line-to-line voltage on the secondary, will work first on the primary. Okay, let's try to bring out the given. The ratio of transformation is 30, step down. It was specified step down. Okay? Because to reduce the voltage, it should be step down, right? And the value of BP line to line on the primary side is 132,000 volts, meaning the line to line voltage on the primary line to line. Okay? So this subscript here refers to primary, and LL is actually line to line between two lines. The value is 132,000 volts. So we needed these two data here to go back to the secondary value. And the requirement is required. What will be the secondary voltage line to line equal to? If the connection on the secondary side is delta. Okay, let's try to bring out the solution. Consider the primary side for the meantime. Okay? For a Y-connected transformer, the one I derived the relationship of the phase voltage with respect to the line voltage, right? There is a relation square root of 3. Okay? And the phase voltage is actually less than the line voltage. And the relation is actually, phase voltage is actually the line to line voltage over square root of 3. Or the line to line in reverse will be square root of 3 times the phase voltage, because the line to line is bigger than the phase voltage. Why is it that the line voltage is greater than the phase voltage? There are two voltages, and we call this phase voltages. So the vectorial sum of any two phase voltage is actually equal to the line voltage. And the relationship is actually this one. The one I derived. Right? So if we now try to compute for the phase voltage on the primary side, we are on the primary side. We are given the line to line, right? So if we try to compute the magnitude of the voltage for each phase, okay, we will be using this relation. So I place it here. The phase voltage on the primary side should be equal to 130,000. This is 132,000 over square root of 3. And this is 76,210. So in each phase on the Y primary, this is 76,200. 76,200. This is 76,200. You add these two here vectorially to get 132,000. You don't add it algebraically. It should be vectorially, because voltages under AC machines are actually complex numbers. You add this one vectorially with this, what comes out is 132,000. But if we are only talking magnitude, the magnitude will be 132,000 over square root of 3. And this is 76,210. Sorry? So we now know the voltage on the primary side phase value. Okay? So we transfer this value here to the secondary. And what will be the required relation? There should be a required relation. Right? To get the relation of the phase voltage on the primary with respect to the secondary, for step-down transformer, okay, to get the relation, we will be using this equation here. For step-down transformer, ratio of transformation is actually, am I still on the camera? Okay, the phase voltage on the primary, phase voltage on the secondary, I place it here, phase values. If you are using this equation here, what you will substitute here, it should be the phase value. It's not the line-to-line value, okay? Because if you try to place the line-to-line value, you are wrong. It should be the phase value. If you are using the ratio transformation, you should use phase values, right? So if we now try to compute for the equivalent phase voltage on the secondary, okay, we'll just compute for this one, right? Vs now, okay, we put this here, and A will be underneath. So this should be the phase voltage on the primary all over A. Okay, to get this value here, we will take this value, we divide it by the ratio transformation. Considering values, phase values, okay? The emphasis is on the phase value. It's not this value here. It should be the phase value. Phase value, that will be ratio transformation. So if we now try to compute for the secondary phase voltage over here on the delta, Okay, it will be the phase voltage on the primary, which is 76,210, and the ratio transformation is 30, right? Step down. So we will divide this by 30. That's why our problem for tonight is example problem is stepping down, right? So this is 76,210 over 30, and this is now 2540 volts. Imagine that one. From 132,000, upon reaching this portion here, it is now 2540. It's stepping down. Okay? So actually, the configuration Y delta is actually for stepping down voltages. Okay? When I discuss the, what they call this application of the different connections. For a Y delta, this is used actually for stepping down. Okay? That's the phase voltage on the secondary. But what is the line-to-line voltage? For a delta-connected secondary, okay, the phase voltage is actually equal to the line-to-line voltage. Why is that so? If you get your voltmeter here, okay, the reading here, okay, should be equal to the reading over here. This voltage here is termed to as the phase voltage, and the voltage at the terminals of the line is actually also V sub L, assuming negligible resistance, right? So whatever you take over here will be the same as here. So for a delta connected transformer, the phase voltage is actually equal to the line voltage. This is a concept. It will not change, okay? For as long as the connection is delta, the phase voltage will be equal to the line-to-line voltage. So what is being asked is actually the secondary voltage line-to-line, and we now know the phase voltage on the secondary, it's 2540. Therefore, the secondary voltage line-to-line will be equal to the secondary voltage phase value, which is 2540. So our answer now will be 2540 volts. Okay, so the output here will now be 2540. Right? From a value of 132,000, by using the connection Y delta and with the ratio of transformation 30, with the given specification step down, we have reduced this 132,000 to a 2540 volts. And this 2540 will now be the input of the secondary transformer, secondary distribution transformer. This is now a distribution transformer. The one connected to the poles before our houses. So the input of the distribution transformers now will be 2540. Okay. Of course, this will be specification step down. So we will, what I call this, divided this one by a certain value. So it depends on the designer of the transformer. For this one to be 120, of course you could compute what will be A. Okay. If you try to order your, what you call this, transformer, and you wanted that the output will be 120, if the input is 2540, what will be the ratio of transformation? You just divide this to here. 2540 divided by 120 equals, the ratio of transformation is almost 22. So meaning to say, okay, there will be 22 turns here. For it to be 120, there will be one turn over here. So if there is a 220 here, okay, 220, there will be 10 here. For it to become 120. So the ratio of this one here will be by the ratio 22, almost 21. So actually, you could design distribution transformer, okay, if the given input is 2540, and for it to be 120 on the secondary, the ratio of transformation will be 21. Okay? So it's a design process, you know. Okay, that's it, guys. That's how we transform a certain big voltage to a lower voltage for the technicians and the, what you call this, clients to be safe. Okay? Because if the input here is 132,000, it's very dangerous. Okay? So we transform this 132,000 to a value 2540 by using transformers which are step down with the ratio 30. So we reduce this 132,000, it became 2540. And the rating of the primary and the secondary transformer now, okay, it will be 2540 and the output will be 120, the one that goes to our houses. And the ratio of transformation, this one, if you try to wound it, okay, the ratio of transformation will be A is equal to 21. Okay? Okay, that's it, guys. That's how we transform a high voltage to a lower voltage by using the configuration Y to delta. Okay, good evening from Los Angeles. This is Professor David J. Delos Reyes.